All right, so this is section 4 of chapter 3, and it's based off of particle motion. We're going to talk about velocity, speed, and rates of change. Now, consider a graph of displacement, in other words, distance traveled versus time. So the distance we traveled is the y value, and the time is the x value. And we've got A and B, 2 points on this graph. The average velocity can be found by taking the change in position over the change in time. Well, that probably looks familiar because it's the slope, and it's the change in distance over the change in time, x. So that means it's going to be the slope of this thing. So your change in position is delta s. It's measured in the y direction. And your change in time is measured in the x direction. So the average velocity in this case could be thought of as the change in position divided by the change in time, or f of t plus delta t. The time t is a, and delta t is how much you're going to go to get to b, minus f of t all over delta t. Now, the speedometer in your car does not measure average velocity, but the instantaneous speed actually, but we think about it as velocity. And that's the velocity at that instant in time. It's not an average over the group or anything like that, or over the trip or anything like that. It's the velocity at that instant. Well, the velocity, the instantaneous velocity, is a very small change in distance over a very small change in time, and that is found by the limit as delta t approaches 0 of f of t plus delta t minus f of t over delta t. Now, guys, this may look really complicated, but it's not. Hopefully it looks a little familiar, because if we change delta t to an h and t to an x, this is nothing more than what? The definition of the derivative. F, the limit is h approaches 0 of f of x plus h minus f of x all over h, which is the definition of the derivative. So velocity is nothing more than the first derivative of the position function. That's something you should file away in your head. Those of you that are taking or have taken physics, you know some of this stuff already. Those that haven't, you're going to have to get a little bit more to remember because they've already learned it. But velocity is nothing more than the first derivative of the position function. Now, let's look at the free fall equation. And we've got s is equal to 1/2 gt squared. Gravitational constants are 32 feet per second squared, 9.8 meters per second squared, or 980 centimeters per second squared. These are just the values for g depending on what your units are that you're dealing with. So if we were to deal with feet and seconds, we could put in 1/2 times 32 t squared, and that right there would tell us how far the whatever has fallen at t time. So 1/2 of 32 is 16, so we end up with s equals 16t squared. Now, if we took the derivative of that, the velocity is going to be 32t. So we could find the velocity at any moment in time by just plugging in t there. Now, one thing you need to know is that speed is the absolute value of velocity. Velocity has a directional component to it. What that means is when I'm talking about a negative velocity, I'm typically talking about moving either left or down, depending on which way we're going. If we're going up and down, negative velocity typically is going down. If we're going left and right, negative velocity typically is going to the left, where positive would be going up or right. Speed is the absolute value of velocity in that it takes the sign out of it. So the sign, since that's your direction, we don't know which direction it is when we're talking about speed. Whatever direction we're going, Speed is just how fast we're going in that direction. Direction is taken out of the thing completely. Now, acceleration is the derivative of velocity, because when we talk about velocity, acceleration is how the velocity is going to change. And remember, a derivative is a rate of change of whatever we're taking the derivative of. So if we take the derivative of velocity, we're finding out how the velocity is changing. Well, acceleration tells us that. All right, and of course velocity, we already know, is the derivative of the position function. So acceleration is the derivative of the velocity function, or the second derivative of the position function. For example, let's say we have the velocity is 32t. The acceleration is 32. Which we already knew that. The gravitational constant is nothing more than the acceleration due to gravity. Now, if distance is in feet, velocity would be in feet per second, feet per minute, something like that. Feet per unit of time. And the acceleration would be in feet per unit of time squared. Because each time we take the derivative, we're telling how that thing is changing. If distance is in feet, then when we find the velocity, we're finding in how many feet is changing every second. And when we do the derivative of velocity, we're finding out how fast the feet per second is changing. So we get feet per second squared. Now, it's important to understand the relationship between the position graph, velocity, and acceleration. So we're going to look at a graph here. You're going to want to make this pretty big because we're going to talk about all this stuff here, and you need to be able to write it in there. All right, so over this first interval here, we're talking once again about distance in my y value and time in my x value. So in this instance right here, what do we know? Well, we know that the distance is increasing, which means we have a positive velocity. Not only that, but it's increasing at a greater rate, so the velocity must be also increasing. Well, right there, this thing the slope is going what? It's going up and it's getting steeper, so that means the acceleration, how the slope is changing, is positive. All right, so let's break this down here real quick before we get too far into this. We know we're looking at velocity. Well, think about this. Velocity equals the derivative of this function we're talking about, distance here. Well, also we know that the derivative is the slope. So when we're talking about the velocity, we're looking at the slope of this and how the slope's behaving. Now, if we're talking about how the slope is changing, that's when we're talking about the acceleration. Acceleration is the derivative of the slope. So we're looking for how is the slope changing. Now what that means is if the slope is increasing, if the slope is getting steeper as we go from left to right, that means our acceleration must be positive, just like we're looking at right here. If the slope is decreasing, like it would be up here, then that means that the acceleration will be negative. And what about when it doesn't change? What about when the velocity or the slope of this thing doesn't change? That means that the acceleration must be 0. So that's what we're talking about. We're talking about the velocity is the slope, and the acceleration is how that slope is changing at that point, over that interval of time. Now, our next interval is going to go over this part right here, and we know that the slope is positive, so the velocity is positive, but it's constant. It's not changing. It's the same slope all the way up through that interval, which means that since the slope is changing, the acceleration must be 0. All right, the next little piece is going to go to the top of this right here, And let's think about it before we see what's happening. What do we know about the velocity? What do we know about the slope? Is the slope positive or negative over this little interval right here? Well, the slope is positive, so the velocity is positive. And what's it doing? Slope is steep here, but it's getting less steep as we go to the top of the hill here. So that means the velocity would be positive but decreasing. And if the velocity is decreasing or the slope is decreasing, what does that mean about the acceleration? The acceleration must be negative. All right, now I'm going to go ahead and I'm going to write where these break, these stop, there, there, there. And I want you to write those into your little graph that you've got on your notes. And I want you guys to try these parts. Describe what's happening. Those four parts, this one, this one, this one, and this one. Describe what's happening. Pause the video, try those out, and then come back and check your work. All right, so for this next interval right here, we know that the slope is going to be negative as we go through there, and it's decreasing. It's getting more negative. So that means the velocity would be negative and decreasing. And if the velocity is decreasing, that means the acceleration must be negative. And of course, right here at the top, the velocity was 0 because the distance wasn't changing right there. We're not going away from or not going closer to at that one instant in time. Now the next interval is going from here down to about here. And what do we notice? The velocity is, the slope is negative, so the velocity is negative, but it's constant. It's not changing. It's not getting any steeper and all that. So that means that the acceleration will be 0. All right, our next interval is right in here. And what do we know? The velocity is, the slope of this thing is negative, but it's increasing. It's really negative here, but it's getting less and less and less negative until it gets flat right there. So that means that the velocity is negative and increasing. And what about the acceleration? Well, if the velocity is increasing, that means the acceleration must be positive. And then this last part right here, what do we notice? We notice that the velocity is, or the slope of this thing is 0, because it's not moving further. It's not, the distance not increasing, not getting larger or smaller. Slope is 0, so the velocity is 0 and constant. And what does that mean about the acceleration? The acceleration would have to be 0 as well. So you need to be able to read a graph like that and figure out what all is going on. All right, so the rates of change, the average rate of change is nothing more than the slope of the secant line. That's all this thing right here is. It's x plus h minus x. The x's cancel out on the bottom. So this is nothing more than y2 minus y1 over x2 minus x1. That's just the difference quotient. Another way of writing the slope. The instantaneous rate of change, you've got to throw that limit thing in there. And we're doing the limit as h approaches 0 of that same thing we had right here, which gives us what? The derivative. So the instantaneous rate of change is the derivative. The average rate of change is the slope of the secant line, the same way it always has been. All right, and these definitions are true for any function. X does not have to represent time or anything. So average rate of change, instantaneous rate of change. All right, so for example, for a circle, we know that area equals pi r squared. Well, if we take the derivative of both sides with respect to r, we get dA dr is equal to the derivative of this side with respect to r is going to be 2 pi r. So what this tells us, you need to be able to read what this means. This says the change in area with respect to the radius is 2 pi r. So when r changes a little bit, that means that the area is going to, this is the rate of change of the area with respect to r. If we want to find how much the area changes, all we have to do is multiply both sides by dr. But that right there is the instantaneous rate of change of the area with respect to the radius. So if we wanted to find the change in the area for a change in r, we would have 2 times pi times the radius but at the beginning of the change times how much it changed. That's what the dr is. Remember, the change in the radius. So for tree ring growth, if the change in area is constant, then dr must get smaller as r gets larger. Right? So if the area of the tree, the cross-sectional area of the tree, if this thing right here is going to grow by the exact same amount every year, then as it gets larger, the change in radius, in other words, how much it adds to the radius of the tree, must get smaller every year, so that the change in area is a constant. All right, that's all of it.